All right, I thought this would be a good learning exercise if you're interested in vintage electronics, but you yourself are not vintage. So you weren't raised on TTL logic and 8080 microprocessors and stuff, but you have an interest and you're kind of resurrecting the old stuff. And you might be familiar with microprocessors or microcontrollers these days, like Arduinos and things. And if you went to go maybe investigate these or troubleshoot these, you might run into some things that just don't look right, all right? So let's go ahead and show you a couple things first, and then we'll talk about why you might be confused, okay? So let me turn this thing on, it's running. Now back in the day, if you were probing around a circuit, you might have something like a logic probe. Now, a lot of people don't have these days. Everything's maybe a oscilloscope or something, but this is a logic probe, and it has a actual light bulb. It's not even LED; it's actual light bulb in here. And if I put it on a signal, you can see it's blinking. Okay, and when I take it off the signal, it doesn't blink. And so that means that there is something changing. There's some type of goes high, low, high, low, high, low. If I go to something that's just high, you can see that the little light bulb gets brighter. That's a high state. And if I put it on ground, it goes to a low state. So when it's off, it's low. When it's high, it's lit. And then in between, it's half lit. Okay, that's called a tri-state condition when it's not connected to everything. So you can see something low, something high, or something changing, okay? And this is really good. You can like examine your data lines. So here's some data lines, and you can say, okay, I've got actual activity on my data line. But let's say that something happened and you no longer have activity on that line. I've held down the reset button and it's no longer clocking, okay? So a lot of times you can take a look at, is maybe the address 12 line, doing something, you can program that and you go, yeah, that's good. Or you can say, okay, I have this chip, which is my ROM. This is the chip select, and I can see that my program's running because my chip select is oscillating. Well, here's an IC, and here's its chip select, and you can see that its chip select is always high, which means it's always deselected. So no part of the program ever tries to access this, right? And so you can get a lot done with just a logic probe, all right? But like I said, not many people have them these days. Raise your hand if that's gone inside your leg before. All right, so let's take a look at, let's see, let me turn my oscilloscope so I can do some probing. And let's see here, let's turn up the brightness and brightness. There we go. So you can see something on the screen. I'm sorry about all the reflections. It's so hard to, yes, I can do screen capture, but it takes a lot of effort. All right, so let me show you a signal. Okay, so this was the signal that I probed that I said, hey, something is oscillating. This is the clock signal, all right? And we can go out and we can say, oh, okay, it looks really good. It looks like a clock, okay? And it's going between 0 volts and about 3.5 volts, okay? You say, well, that's a little bit low. I'm not sure about that one, but that's okay. I guess that's just the way it is. Let's go take a look at one of those data lines, okay? Here's a data line. And we can see that it's doing stuff, right? And if we did a single shot, you could see that it goes high and it goes low and it goes high and it goes low. So we're sending data. Some of the highs are not quite as high as the other ones. So there's some that are not as quite as high as the other. And so you're probing along and say, yeah, oh, wait a minute, these are kind of low. And you kept probing around your data lines until you get to this one and you just go, oh my goodness, there's something wrong. My circuit's just completely busted, okay? it's actually just fine. Okay, so that's what I want to talk about today. I want to talk about what does it mean to be a 1 and what does it mean to be a 0, okay? So let's take a look at a chart here. And this is a TTL range of voltages. So for a TTL output, a gate output, it can go somewhere between 2.7 volts and 5 volts. So if your TTL output is somewhere between 2.7 and 5, it's just fine. It's within spec. And if it's below 0.4 volts, it's still within spec. Now, an input, a TTL input, says anything above 2 volts is a high, is a 1, and anything below 0.8 volts is a 0, okay? And so let's go back up to our picture here. Let me put the data back on it. Let me just grab one. All right. So if I put some markers on, I have some markers set here. Turn the marker. I think that box. I want to get rid of the box. I'll use my mouse. Use my mouse. All right. So I've set marker lines at 2 volts and 0.8 volts. All right. So if your signal is above 2 volts, it's a high. And if it's below 0.8 volts, it's a low. And so as we probe around, we can see that all that stuff that looks like it's broken is actually way above 2 volts. And so it's still considered a high. All right. Some lines are gonna look pretty nice. They're not gonna look too bad at all. Some of them have kind of a different structure. So as you probe around an old TTL or old NMOS type system, look at this one. This one has 4 levels. Yeah, look at that. But they're all above 2 volts. Now, why is that? Why was the old days so bad? Why was the old days? Why couldn't those guys get it right? Let's take a look at some stuff. All right. Here's what you might be used to in modern day. This is a CMOS chip. All right. And it's actually a pretty old CMOS chip, but it's CMOS. And if you take a look at how it's constructed, this is A and B, and then this is the output Q. And you can see that there's a transistor on the output that can pull it high, and a transistor on the output that can pull it low. And so it can pull it high really good, and it can pull it really low really good. All right? But what about the old days? All right, here is the gate of a 7400, okay, a NAND gate. And this is the schematic of that NAND gate. And you can see that the output here has a transistor that can pull it low, a transistor that can pull it high. But you'll notice that they are bipolar transistors, right? CMOS hasn't been invented yet. And so what is the voltage drop of a transistor? It's called VSAT. So what is your saturation voltage of this transistor, right? Well, it's around 0.4 volts, right? As long as it's below 0.4 volts, your output specification is correct. So it could pull it down pretty good. But look at the upstate. It goes through a diode, and then it goes through a transistor, and then it goes through a resistor. So it doesn't pull up very good. And as you start loading down the input, it really can drag this down. So you can never quite get to VCC. It's got all this stuff in the way. But that's just the way it was back then. And things just weren't great. Let's take a look at some of the numbers in the data sheet. All right. This says high level input voltage. There it is, 2 volts. Low level input voltage, 0.8 volts. So you need to be somewhere between 2 volts and 0.8 volts. But look at this. We can drive low. We can drive 16 milliamps low, but driving high, 0.4 milliamps. It just can't pull up very hard. It just can't. And so that's when you start getting in trouble if you start loading this thing down, called fan out. But as you have more and more stuff on this output, you can only supply 0.4 milliamps. And so you just really can't drive much. All right. We can look at some other numbers here. Here's your voltage high, your voltage low. Somewhere, worst case, it's 2.4 volts, and worst case, it's 0.4 volts. So again, we're within spec. Let's see here. Okay, what about as time goes by, there was the 74LS00, the LS parts, okay? The LS parts were, again, 2 volts and 0.8 volts. But look at the drive conditions. 0.4 volts high, but only 8 milliamps low. It got worse. It didn't get better, it got worse. So when you're operating with LS parts, you can only drive low 8 milliamps. Yeah, so yeah, it got worse. CMOS chips these days, gosh, they're like 24 milliamps or something. They're ridiculous. They're like really good. Plus or minus 16 milliamps is typical for some things. And then this data sheet just includes a couple parts. Here's a fun one, a 74S, the Schottky version. 74S, again, it's 2 volts and 0.8 volts, but you can drive high much better, 1 milliamp, and you can drive low much better, 20 milliamps. So yeah, but if you go back to the good old days, you're talking about, 8 milliamps down and 0.4 milliamps up, and that's what you see here. It's able to pull down pretty good. We never really saw any issues pulling down, but all of these issues about pulling up, some things are loaded more. There's talking to different machines and talking to different signals and things. And so sometimes you can pull up really good because there's not much load on it, and sometimes there's lots of load on it. You only get around 3 volts. And so, but it's still within spec. The spec was set because of this. It was set at 2 volts because you're going to have all of this noise in here, right? All right, let's go ahead and turn it back on. So anyway, when you're probing around, don't be too scared if you see something like that, thinking that, oh my goodness, it just must be broken, right? You expect to see, what was that I just looked at? Yeah, you expect to see things like this where everything looks wonderful. And then you go over here to something like that and you go, well, not too bad. And then you go over here and you go, oh, that's not too good. And then you look at that and you go, okay, it's broken. It's broken. But it's not. It's just the old days. Us old geezers had to deal with that.